Alright, let's get right into it. What we're doing here is a forensic analysis of a critical, and I mean critical, point of failure in major industrial expansions. We are de-risking the schedule for new magnetics facilities, and we're going to do that by focusing on the one area that is constantly dangerously underestimated, the tank farm. You know this quote, and it really hits on a huge fallacy that delays billion-dollar projects. All the attention, all the high-CapEx focus goes to the big ticket items, but the real schedule killers, they're treated like a commodity, an afterthought. This analysis is here to correct that oversight. So the core risk in a magnetics plant expansion isn't the primary process equipment. Nope, it's the chemical storage and handling infrastructure that has to support it. Your most expensive delays are hiding right here in the tank farm. It's the area that gets specified last, and it's the area that gets budgeted the least. So we've identified three primary ways these projects get derailed. We're calling them expansion killers. The first one is process contamination. And look, in magnetics manufacturing, this isn't some minor issue. It's a direct threat to your product yield and your quality. For high-performance neodymium magnets, the plating process, it's everything. The purity of that nickel sulfamate bath is absolutely non-negotiable. Any organic leachables, any particulate coming from your storage tanks, they can cause catastrophic plating defects. We're talking about a direct hit to your final product's magnetic properties and its yield. Now take a look at this. The difference in the material architecture here is fundamental. A traditional FRP or fiberglass tank is a composite. It's made of layers, resin, glass fiber. An extrusion wound wall, on the other hand, is monolithic. It's one solid material. And that distinction is absolutely critical when we talk about process purity. You see that layered construction of FRP tanks? It basically introduces multiple failure modes that are going to compromise your high purity chemicals. You've got resins and plasticizers leaching into the nickel sulfamate. You get something called fiber bloom, which releases microscopic glass particles. And then there's osmotic blistering, which traps and later releases degraded chemicals right back into your process. The result is always the same: reduced yield and compromised quality. So that brings us right into expansion killer number 2, structural instability. This is a massive risk, especially for any facilities being built in high wind or seismically active zones. And here you can see the difference between an afterthought and a fully engineered system. A commodity tank relies on external cables for anchorage. The problem is they are prone to what's called cheese wire failure under shear stress. The cable literally cuts right through the tank wall. But an engineered system, it integrates structurally welded lugs right into the tank itself, designed to meet very specific ASCE. That structural integrity, it pays off in another huge way. Because the walls are so thick and monolithic, we're talking up to 3 inches thick, they can support heavy industrial equipment directly. Think about this: a 1-ton industrial mixer mounted right on the tank shell with no need for costly space-eating external steel support structures. That fundamentally changes your plant layout and your budget. And this structural integrity is not just a claim, it's validated by adherence to DVS 2205. That's a really rigorous German engineering standard. It mandates specific safety factors and fabrication procedures to ensure predictable, reliable performance under extreme stress. This is the engineering that backs up the tank stability. And that leads us to the third and maybe the most immediate threat to your project timeline: commissioning and civil engineering delays that are literally baked into the equipment specification itself. The data here is, well, it's stark. The typical lead times for traditional FRP or steel tanks have ballooned. We're seeing 20, sometimes 30 weeks. By specifying them, you are baking a month delay into your schedule before a single shovel even hits the ground. Compare that to the 4 to 6 week lead time for extrusion wound tanks. This isn't just an optimization. It's a strategic arbitrage against your commissioning clock. And it's not just about procurement. The installation itself is a sequence of potential delays. Traditional tanks, they often need poured in place concrete for secondary containment. So that means you have to design the berm, pour it, and then wait a minimum of 4 weeks for that concrete to cure. The whole process is completely at the mercy of the weather, and it involves multiple contractors and complex coordination that can just easily spiral out of control. So now that we've analyzed these 3 failure vectors, these 3 expansion killers, we can actually define the architectural solution. The goal here is to eliminate these risks right at the specific stage before they can implement killers simultaneously. The contamination risk is eliminated by a monolithic inert material. The instability risk is gone thanks to a DVS 2205 compliant engineered structure, and the delay risk is eliminated by rapid lead times and solutions that completely bypass all that civil work. You know, when you zoom out and you look at the facility as a complete system, the tank farm's central role becomes undeniable. It's the hub. It connects your entire plant's utilities, everything from the chiller yard to wastewater to hazardous material handling. Its design is not an afterthought. It is foundational to the entire site's civil and utility plan. So the final question is this, and it's for you to ask your team. Have you reviewed your tank architecture before you lock in the civil and utility plans? Because that single decision made early on is what will determine whether your expansion schedule slips by an entire quarter. It's a decision that has to be a deliberate one.